Welcome to Future Talk. On today's program, we're going to talk about earthquakes. Earthquakes have been very much in the news lately, especially with the recent 9.0 earthquake in Japan, and a lot of places in the United States, especially on the West Coast, are also vulnerable to quakes. We're going to talk about the science of earth movements, new advances in predicting quakes, methods of preparing for quakes, and ways of responding to them. I have two guests. In the second half of the show, I'll be speaking with Kevin Montgomery, CEO of Intelesense Technologies, which provides a global integrated monitoring service for managing all kinds of disasters, including earthquakes. But first, I'll be speaking with Jeanne Hardebeck, a research geophysicist on the earthquake hazards team at the U.S. Geological Survey. Jeanne Hardebeck has a PhD in geophysics from Caltech, and her awards include the Presidential Early Career Award for Scientists and Engineers, the James B. McIlwain Medal from the American Geophysical Union, and the Charles F. Richter Early Career Award from the Seismological Society of America. Jeanne, welcome to the program. Good to have you today.
Thank you very much.
Now, what do we actually know about the cause of earthquakes? I understand that it has something to do with tectonic plates. What are they exactly?
That's correct. So we usually think of the Earth as being made up of hard rock. And that's true of the outer part of the Earth, which we call the lithosphere, or the rock part of the Earth. And that part of the Earth is actually floating on top of rock that flows like very slow molasses. And it's this lithosphere, this hard rock part of the Earth, that is divided up into a number of plates. For instance, North America is a plate. The Pacific Ocean is a plate. And where these plates move past each other as they float on this sort of slow molasses rock is where we tend to have a lot of earthquakes. And the recent earthquake in Japan occurred because the Pacific plate is diving down under the islands of Japan.
Now, if the Earth is covered with a solid crust, how does it get broken up into separate pieces? And why aren't all of these tectonic plates moving in unison over this soupy stuff below the surface?
So the soupy stuff below the surface is actually very hot, and there's heat trying to escape from the Earth. And this heat then causes upwellings which push these plates apart away from each other, and then we end up with places, for instance, in the middle of the Atlantic Ocean, where new crust, new lithosphere is being created. So in places like Iceland, for instance, where there's a lot of volcanoes, those volcanoes are making the new crust and pushing those two plates away from each other.
So if two plates move away from each other, the molten material between them will cool off with exposure to air.
Right, right. And so there's that's one of the forces driving the plates, and the other force driving the plates is eventually these plates cool, and the cooling plates are heavy and descend down back into the Earth. So that's what's actually happening under Japan, that this thick, cold Pacific plate is diving down under Japan because it's cold and dense and falling towards the center of the Earth.
Now, if the tectonic plates meet at the edges going in opposite directions, does that mean that if you live in the middle of a tectonic plate, which might be 5,000 miles in diameter, you're relatively safe? Is it only at the edges of the plates where there's an earthquake danger?
Most of the earthquake danger is concentrated near the plates, but there are actually large earthquakes that occur inside the plates. And a famous example of that are the New Madrid earthquakes that occurred near Memphis, Tennessee in 1811 and 1812. And these were very large earthquakes that were very destructive and felt over much of the east coast of the United States.
Now, how solid are these plates? Are they pretty cohesive, or are they just riddled with faults all the way through, not just at the edge?
They're fairly cohesive, but there are faults within the interiors of these plates as well.
Now, there was recently this huge earthquake in Japan. It killed many thousands of people, 9.0 on the Richter scale. And a lot of people who live in California want to know, what's the chance that we would have a comparable earthquake here?
So in the northernmost California, from about Mendocino north up through Oregon, Washington, and into British Columbia, is a subduction zone pretty much just like the subduction zone in Japan. And in our case, this is a remnant of another plate next to the Pacific plate that's diving down now under North America. And we have actually had an earthquake very similar to what just occurred in Japan in the year 1700. So that earthquake we actually know a lot about because it caused also a large tsunami over the Pacific Ocean and was recorded in Japan.
I think we actually have some slides which illustrate what California looks like from an earthquake perspective. So maybe we'll take a look. Okay, so there's the first, well, it was there. Can we see that first slide again? There it is. So what is that slide telling us exactly?
So this is a map where we are looking at the probability of a magnitude 6.7 or greater earthquake in California. And a magnitude 6.7 is about the same size as the 1994 Northridge earthquake in LA, or a little smaller than the Loma Prieta earthquake here. And you can see that the bright colors, the red colors, where we see the highest probability, are mostly focused along the San Andreas Fault, along the coast of California, and a little bit on the eastern side of the Sierras.
When you say there's a certain percentage likelihood of an earthquake in California, is there a distinction between northern or southern California? Because California is a large state.
So this is what this map is meant to show, that the regions where you see the warmer colors are the regions where these earthquakes are more likely. So we think that there's actually pretty much a 99% probability that there'll be a magnitude 6.7 or greater earthquake somewhere in California over the next 30 years. But most of that likelihood is concentrated along this Cascadia subduction zone in northernmost California and along the San Andreas Fault system.
Okay, let's take a look at the next slide. Do we have no? Okay. So this looks like the San Francisco Bay Area, more or less.
Right, so this is focusing in on the San Francisco Bay Area, and we think that there's a 63% chance of a magnitude 6.7 or greater earthquake within the next 30 years. So I think of that as sort of the probability of a large earthquake in the Bay Area during the rest of my career as a seismologist. So looking a little bit at at those numbers on the particular faults, you can see that the fault we're actually most worried about is the Hayward Fault in the East Bay.
And when you say that there's a certain probability of having an earthquake of that magnitude, how much damage would an earthquake of that magnitude do? Because that's not nearly as big as the one they just had in Japan.
You're right, it's not as big, but it would be even closer to where people are living. So, for example, there was recently a damaging earthquake in Christchurch, New Zealand that was about this size that happened to occur in the city of Christchurch and was quite damaging and killed a number of people. So I believe my third slide is a comparison of...
There's the third slide.
So the third slide is a comparison of the shake. On the left is the shaking that we experienced in the 1989 Loma Prieta earthquake. For those of you who lived in the Bay Area back then, we all remember that that was quite a destructive earthquake, particularly in the Marina district. But we can see here that most of the shaking in that earthquake was actually focused in Santa Cruz. On the right is a scenario of a similar sized earthquake occurring on the Hayward Fault, and you can see all of the bright colors, which are the heavy shaking, occur along the East Bay in these very heavily populated areas such as Berkeley and Oakland, Fremont, and also down to San Jose. So this earthquake, a same size earthquake but on the Hayward Fault, could be actually much more destructive in the Bay Area than the Loma Prieta earthquake was.
Are we pretty confident that we know where all the fault lines are, or could we be discovering new fault lines that we didn't know about?
We know where most of the largest faults are. We do discover new faults all the time, and sometimes we do discover them when they have an earthquake. The 1994 Northridge earthquake in LA area is an example of that, and we can also find them through various sorts of seismological studies and other sorts of geological studies. We can find these faults before they have a damaging earthquake.
Okay. Now, one feature of earthquakes that is often very damaging is tsunamis. They had a huge tsunami in Japan. Now, we live along the Pacific coast here in California. What causes the tsunami? Why is there suddenly a huge flood that sweeps everything in its path?
So when we have the type of earthquake where the seafloor actually moves, and this is what happened in Japan, the seafloor moved as one of these plates went under the other, that displaces a fair amount of water, and it's the same as if you splash in a bathtub or something.
It moves in the vertical direction.
Or you move the water vertically, and that starts this wave. And these waves travel very efficiently across the ocean, as we saw that this earthquake from Japan actually did damage, for instance, in Santa Cruz Harbor. So
now, when the plate moves up and spills water all over the land, does the plate always go back to its original position, Or does sometimes that water stay there and that land area remain permanently submerged?
That can happen, and we saw in Japan, in the Sendai area, that the land surface went down, I think, about 5 feet, and that means that a certain amount of land there now is just permanently underwater that was not underwater prior to the earthquake.
Was it much land or just a tiny little...
I don't know exactly, but it's quite flat in the Sendai Plain, so it's probably a fair amount of land that's now permanently flooded.
Now, we expect earthquakes here in California. Is there any advice you can give on what people can do to be better prepared for a quake?
So the thing I usually think of is to be prepared to basically camp in my house for a couple of weeks. So my sister-in-law is actually from Sendai, and she has family there, and they have not gotten supplies in yet from the outside world.
And so Sendai was the city in Japan that was hardest hit by the quake.
That was hardest hit by the quake. So they are basically camping in their house out of the supplies that they had prior to the earthquake. So it's really important to have enough drinkable water because you don't know that the water supply will be there for you. It's a good idea to have food for a couple of weeks, and food that you're not relying on having gas and electricity to be able to cook. Good idea to have flashlight, like a hand crank radio, so you can keep informed about what's going on.
Lots of batteries,
Lots of batteries, extra clothes, warm clothes. It's been a problem in Sendai that it's been very cold and even snowing now. So people who've lost their homes have found themselves very cold out in the snow, very cold in the shelters, and so it's very important to have some warm clothes somewhere, blankets, things like that.
Now, one of the biggest dangers of an earthquake, one of the most common causes of injury and death, is when things fall on you.
Mm-hmm.
Is there anything you can do to reduce the likelihood that you're at home and things just fall on you?
That's true. You can go through your home and you can look at things that might fall on you, like bookcases, and you can strap those things to the wall. It's a good idea to strap your water heater to the wall because that can be quite bad if your water heater rips out and falls over. So it's a good idea to, before an earthquake, look around your house at what might fall on you, and also look around your house for a place to go in case when you start feeling the shaking of an earthquake. And the best place to go is to find, a good sturdy table and just get under that good sturdy table, so if things do fall, they can't injure you.
And you think most Californians are sufficiently aware of these issues that they would be properly prepared?
I would think that most Californians are aware of earthquakes, but the statistics we've seen is only about 10% of people in the Bay Area have actually made preparations for the earthquake. And even though I show probability maps saying the probability of an earthquake, that's talking about the probability of the earthquake over the next 30 years, because these earthquakes will happen. They definitely will happen, and it's just a matter of when they happen. So we need to be prepared when they do happen.
Okay, very good. We're going to go to the next segment of our program. I'm going to be talking to Kevin Montgomery, CEO of Intelesense Technologies. But first, we're going to watch a short video of some of the damage done by the earthquake and tsunami in Japan. Let's go ahead and roll that tape.
Very high tsunami are expected in the following areas: the Pacific coast of Aomori Prefecture, the coast of Iwate Prefecture, the coast of Miyagi Prefecture, the coast of Fukushima Prefecture, the east coast of Chiba Prefecture, the eastern part of the Pacific coast of Hokkaido, the central part of the Pacific coast of Hokkaido, the coast of Ibaraki Prefecture, the coast of the Izu Islands, the western part of the Pacific coast of Hokkaido. The waves can be more than 3 meters high in some of the areas mentioned. Everyone near the coast must evacuate to higher ground. The Meteorological Agency is also warning that tsunami are expected in the following areas: the west coast of Chiba Prefecture, the coast of Kanagawa Prefecture from the entrance to Tokyo Bay to the west, the coast of Shizuoka Prefecture, the coastal areas facing Tokyo Bay, the coast of the Ogasawara Islands, the coast of Mie Prefecture south of Ise Bay, the Sea of Japan coast of Aomori Prefecture, the Pacific coast of Aichi Prefecture, the coast of Wakayama Prefecture.
That was a video of some of the damage done by the recent earthquake and tsunami in Japan. And I'm now talking to Kevin Montgomery, CEO of Intelesense Technologies, which provides a global integrated monitoring service used for managing the response to all kinds of disasters, including earthquakes. Kevin is also the director of the National Biocomputation Center at Stanford University, where his team develops advanced medical technologies for NASA, the Defense Department, the National Institutes of Health, and many other organizations. He has a PhD in computer engineering from the University of California at Santa Cruz. Kevin, welcome to the program.
Thank you.
Good to have you today.
Thank you for having me.
Now, I understand that your field is disaster management. What sort of work do you do in disaster management, specifically as it involves earthquakes?
Well, specifically with earthquakes, what we've learned is that you need to integrate a lot of information to attain situational awareness of what's really going on in an area, no matter whether it's an earthquake as a disaster or any other sort of natural disaster. So specifically with the case of Fukushima and the Sendai and Japanese earthquake, what we've been able to do is rapidly integrate all of the other information that exists in the world that could be of value to let people understand what's happening on the ground there and be able to make informed decisions about that.
Now, when you say you integrate all this information, where do you get it from? What's your source?
Typically, it's a lot of different information sources that are popping up over the internet. So for example, to relate back to the previous speaker, we automatically tap the USGS shake map and all of their sensors that exist worldwide. We also automatically tap the NOAA ocean buoy network worldwide, so we can actually watch the tsunami as it travels across the Pacific. We can tap all kinds of different information sources that exist out over the internet, but each one are in their own little stovepipes within their organizations. What our service does is it lets you integrate all that data together to basically put all the world's data at your fingertips about any particular event.
Are you involved in generating any of your own data, or is it all gathering data generated by other sources?
No, we also have our own sensors that we've deployed worldwide that sometimes you need information about a particular area, and so you would like to be able to actually place a sensor there. So in the case of Japan with the Fukushima reactor issue, being able to place sensors actually on the ground there that are radiation detectors together that are integrated with weather stations, so you can know which direction the winds are blowing. So we also make those sensor stations, and we have them deployed worldwide for problems from waterborne illness to air quality to also radiation.
Now, don't your sensors also detect Earth movement?
They can. We can also plug in any sort of other sensor also, so accelerometers and other detection methods as well.
So these sensors all send their information electronically, so you basically have an electronic transmitter, and on top of it you can have a sensor that looks for some particular type of thing, and then it sends it to the central source.
Correct. Basically, we've made a box, an electronics box, that lets us plug in pretty much any kind of sensor, weather sensors, water quality, seismic sensors, anything, and then it can transmit that data from anywhere on the planet. But what you really need to do is integrate data together from those sensors that you know about, but also everybody else's sensors too. And the idea is, again, if we integrate all of the world's data into one place and then put it at the fingertips of those that need to make rapid decisions, then it becomes a very powerful tool.
Is it possible that there is so much data that it's hard to find what you want unless there's also a method of organizing it?
Absolutely. That's one of our largest challenges. Is our service right now has over 800,000 layers of live data streaming into it right now, and you can easily become overwhelmed by all that information. So that's been one of our big challenges we've been working on, is to call out just those layers that are really important for a particular topic.
Now, you have your laptop here, and I understand that you're going to give us a demonstration of your product. So let's take a look at what you've got here.
Sure. So this is called IntelliView. It's a worldwide visualizer, kind of like Google Earth, but different in a number of different ways. What I've brought up here is kind of a world overview, and first I thought I would take us to Japan. So this system right now is integrating online media information and all kinds of data about the situation that's occurred there. And as I turn on different layers, I can look at the affected areas within Japan and see the nuclear power plants that have been affected. In fact, let me even zoom in a little bit here.
Is this all updated automatically in real time?
Absolutely.
Without
updated live.
Human intervention?
Correct. Without any human intervention, this is all updated. So this is live data coming in from the USGS feed. Live media reports also coming in related to the nuclear reactors there. Information about from media sources also about the airport, YouTube videos, all kinds of information. So in this case, we've integrated just the affected locations. But what's also interesting is we have all of the Japanese shelters. So this is a rather large, what's called KML file, which is actually only available in Japanese. And unfortunately, I don't have the Japanese language pack here, so you can see this written in Japanese. But we do real-time translation of all of this data as well. So here, in this one portal, which anyone can go to, it's fukushimacrisis.org, you can zoom in and click on any location, and it'll tell you information about that shelter and then integrate that together with other information that's going on.
Now, how do people access this? Is this a free service that anybody can access anytime they want?
Absolutely. So Intelesense does a lot of environmental monitoring projects for National Science Foundation. We do other projects for other clients. But when there's something as important as Fukushima and the crisis in Japan, we absolutely put all this data out there, because through sharing information, we can all make much better decisions. So this is completely free. Go to fukushimacrisis.org and feel free to use all of the information that's there.
Now, who else uses this? For example, do public safety organizations rely on this type of product?
Absolutely. So we're getting involved more and more with disaster management. So for example, we were heavily involved with the Haiti earthquake, being able to rapidly integrate all of the information that everyone in the world had, from satellite imagery to medical facilities to where the areas of greatest damage were, and then bring all that data together and then make it available to folks at WHO, World Health Organization, Department of Homeland Security, Department of Defense, State Department, and others, so that we can manage and understand what's going on in a crisis.
So the system has been field tested already, and it's been shown to work okay.
Absolutely, it has been. In fact, what I did on this other view is I actually brought up Port-au-Prince, Haiti. So just jumping from the Fukushima crisis portal, jumping over to Haiti, during the break, I went ahead and integrated in a bunch of different information that we happen to have from there. And I can go all the way down to viewing individual satellite images and look at before and after, look at where all the medical facilities are, look at all of the tectonic plates and how that played in with the shake maps, and even manage a response.
So does this also include information like, let's say you're in the earthquake zone, you want to know what roads are still open, is gasoline available, or bridges able to be used? So it has all that kind of information. What medical services still exist, what hospitals are still open?
Absolutely. What happens typically is that different organizations will take that information and put it online on a website. But nobody's really integrated all that information together and made it easy for you to have kind of one-stop shopping to be able to get all the information that you could need. So that's really what our integration service does, is again, integrate all this information together so you can make informed decisions.
Now, who supports it all? Because you must have a fair number of employees and you must have expenses. Is the government funding it, or?
We're actually a relatively small team. We have about 15 engineers, all from NASA and Stanford, that have been developing this, and it's actually spun out of my lab at Stanford. But we have really great collaborators all over the world with different universities and different places, different government labs. A lot of our funding actually comes from the Department of Defense, but it's more for force health protection. So radiation monitoring in Japan, for example, being able to transmit medical data from anywhere in the world, being able to, again, make better decisions as a leader within the military is also important. Even real-time air quality, so that our troops aren't subject to toxins and stuff in the environment.
Now, does this help to predict earthquakes? You have all these sensors around the world which can detect earth movements. Is that helpful in indicating when an earthquake might be likely to occur? Are there certain signature types of movements that would occur shortly before a big quake?
Well, that's a good point. The next step, really, right now we're in the data acquisition phase. And as I said, a lot of data is being acquired and it tends to stay within its own stovepipes. Now that we've started to integrate things together, we can start to look at how different things are correlated together. And once we have all of that information, we can then do the next step, which is real-time analysis and modeling and looking at all of those correlations and seeing how they may impact each other.
Does this also help coordinate the disaster response, like as far as dispatching the ambulances? Where should the rescue teams go? And how can the different public service agencies coordinate with each other? Does this provide the tools to do that as well?
One of the big problems with, for example, Hurricane Katrina is that the people in Washington didn't understand what was going on the ground in New Orleans and other places. A tool like this allows everybody to literally get on the same page. And so it does allow you to communicate up and down the chain and also across organizations. So that is the next step for us, and we're talking with a number of groups about doing exactly that.
Yeah. Do you see this as becoming something that's used worldwide, or there other people doing similar types of projects? Because it sounds like it doesn't require that much of an initial investment to get started with this type of...
Well, that's what we do. We actually make this platform available to anyone that for a good cause, basically. And that's what we want to do, is to really facilitate groups of people distributed perhaps around the globe to come together and work together to solve big problems, or to manage disasters in this case.
So I think this might lead to more international cooperation in general. So for example, if people in America have a better understanding of what's going on the ground in Haiti or Japan or someplace else, they could better tailor their own response to it if they're going to have a response to it.
Well, certainly. I mean, in the case of Haiti or Japan, it's a very good example. It's a multinational effort. In the case of disasters, or in the cases of a lot of the tasks and the challenges that we face, from climate modeling and the changes that happen because of that, to even natural disasters like this. Our ability to work together across organizations is really important, and all we're trying to do is to facilitate that.
And you're the main organizer of this project, who's basically put the software together. What's your role in it?
I'm the leader of the band. I've got a great group of engineers, and again, a great group of collaborators that we work with all around the globe. And we don't compete with anyone. We just collaborate with everyone. So as I said, it looks a lot like Google Earth. Someone can use Google Earth to view this. The idea is to, again, bring people together and solve big problems and do big things.
Well, great. It sounds like you're making good strides for something that really needs to be done. I've just gotten the signal that we're just about out of time, so we're going to have to wrap the show. I'd like to thank my guest, Kevin Montgomery, CEO of Intelesense Technologies, also my earlier guest, Jeanne Hardebeck of USGS. Please visit us at our website at www.futuretalk.net. This is Marty Wasserman for Future Talk. Be sure to tune in again next time, and we'll see you next time.